There is a single machine, one machine, without which your phone doesn't exist, your car doesn't start, the global financial system collapses, modern medicine grinds to a halt, and every military on Earth goes blind. This machine costs $380 million. It weighs 180 tons. It takes 40 freight containers and 3 Boeing 747 cargo jets just to deliver one. Only one company on the planet knows how to build it. And right now, there are fewer than 100 of them operating anywhere in the world. If you destroyed every single one of these machines tomorrow, human civilization as we know it would begin to unravel within weeks. Not months, weeks. And yet almost nobody knows this machine exists. It's called the EUV lithography system. EUV stands for extreme ultraviolet. And it is, without exaggeration, the most complex device ever engineered by human beings. More complex than the space shuttle. More complex than a nuclear submarine. More complex than the Large Hadron Collider. But here's the thing that should really bother you. You interact with the output of this machine hundreds of times a day. Every time you tap your phone screen. Every time your laptop processes a thought. Every time a satellite locks onto your GPS signal. The chips inside those devices, the ones with transistors smaller than a virus, smaller than a wavelength of visible light, those chips are only possible because of this machine. So how does it work? How did one company, in the flatlands of the Netherlands, become the most critical choke point in the entire global economy? And why are governments around the world now treating this machine as a matter of national security? To understand that, we need to start with a problem that nearly broke the entire semiconductor industry. For decades, making computer chips worked on a beautifully simple principle. You take a beam of light, you shine it through a stencil, called a mask, and that light projects a pattern onto a silicon wafer coated with a light-sensitive chemical. Wherever the light hits, the chemical changes, and you can etch circuits into the silicon. It's a lot like developing a photograph, just absurdly, impossibly precise. The rule was straightforward. If you want smaller transistors, you need shorter wavelengths of light. Shorter wavelengths can draw finer lines. For years, the industry used deep ultraviolet light with a wavelength of 193 nanometers. Engineers squeezed every last drop of performance out of that wavelength. They invented immersion lithography, putting water between the lens and the wafer to bend the light tighter. They invented multiple patterning, exposing the same wafer multiple times at different angles to carve features smaller than the light itself should allow. But by the early 2010s, they hit a wall. Physics itself said, you cannot go smaller with this wavelength. Not practically, not economically. The workarounds were getting so complex, so expensive, that the cost of making chips was starting to outrun the benefit of shrinking them. Moore's Law, the engine that had driven the entire digital revolution for half a century, was about to die, unless someone could find a fundamentally new kind of light. And that's where this story gets insane. Because the light they needed, extreme ultraviolet, with a wavelength of just 13.5 nanometers, doesn't just exist in nature in a useful form. You can't generate it with a lamp. You can't generate it with a laser diode. You can't even generate it in a vacuum tube. To create EUV light, you need to do something that sounds like science fiction. 50,000 times per second, a high-powered carbon dioxide laser fires at a tiny droplet of molten tin. Each droplet about 25 microns across, roughly the diameter of a human skin cell. The first laser pulse flattens the droplet into a pancake shape. A second, far more powerful pulse hits that flattened target and superheats it to around 500,000 degrees, roughly 40 times hotter than the surface of the sun. At that temperature, the tin becomes plasma, and that plasma emits light at exactly 13.5 nanometers. But here's the catch. Only about 1% of the energy in that plasma comes out as usable EUV light. 1%. So the machine generates this light 50,000 times a second, captures the tiny fraction that's useful, and directs it through the most precise optical system ever built. And those optics? They can't be traditional lenses. EUV light is so energetic that it gets absorbed by virtually everything, including glass. So instead of lenses, the machine uses mirrors. But not ordinary mirrors. These are multi-layer mirrors made of alternating atomic thin layers of molybdenum and silicon, stacked about 100 times. The surface of each mirror is polished to a flatness of less than 1/10 of a nanometer. If you scaled one of these mirrors up to the size of Germany, the tallest bump on its surface would be less than 1 millimeter high. There is no room for error. None. The machine that does all of this is built by a company called ASML, headquartered in Veldhoven, a quiet town in the southern Netherlands. And the story of how ASML came to monopolize this technology is as unlikely as the machine itself. ASML was spun out of Philips, the electronics company, in 1984. It started with a handful of engineers in a wooden shack next to a Philips factory. They weren't the market leaders. Not even close. Japanese companies like Nikon and Canon dominated lithography equipment. ASML was an underdog, building machines for a market that was already crowded. But ASML made a bet that changed everything. While Nikon and Canon tried to develop EUV technology mostly in-house, ASML built a web of partnerships. They collaborated with Zeiss in Germany, the only company capable of manufacturing those impossibly precise mirrors. They worked with Trumpf, also in Germany, to develop the insanely powerful laser system. They partnered with research institutes, universities, and chip manufacturers across 3 continents. The development of EUV lithography took over 20 years. 2 decades of engineering, dead ends, breakthroughs, and billions of dollars in R&D. There were years when serious people in the semiconductor industry said it would never work. The light source wasn't powerful enough. The mirrors degraded too fast. The tin droplets couldn't be targeted accurately enough. Every individual problem was a moonshot to solve, and all of them had to be solved simultaneously. But ASML persisted. And by the mid-2010s, they had a working machine. Today, ASML is the sole supplier of EUV lithography systems on Earth. There is no second source, no competitor, no alternative. Nikon and Canon abandoned the effort years ago. The barrier to entry is so astronomical, the web of suppliers so specialized, the accumulated knowledge so deep, that no new competitor could realistically enter this market for at least a decade, probably longer. Let that sink in for a moment. Every advanced chip made by TSMC, Samsung, and Intel, every processor in every flagship smartphone, every AI training chip, every data center GPU, runs through ASML's machines. One company, one town in the Netherlands. This is why governments care. The United States pressured the Dutch government to block the sale of ASML's most advanced machines to China. Not tariffs, not trade restrictions, an outright export ban. Because controlling who gets access to this machine means controlling who gets access to the most advanced computation on the planet. It is arguably the most consequential piece of technology on the modern geopolitical chessboard. And ASML isn't standing still. Their newest system, high-NA EUV, pushes the resolution even further. It has a larger numerical aperture, meaning it can print even finer features. This machine weighs over 150,000 kilograms and costs more than $380 million. It arrives in pieces, and it takes months to assemble and calibrate on site. The precision required is so extreme that the factory floor where these machines operate must be isolated from vibrations, including vibrations from traffic on roads hundreds of meters away. So here's the picture. The most consequential technology of the 21st century, artificial intelligence, autonomous systems, advanced communications, military intelligence, medical diagnostics. All of it depends on advanced semiconductors. And advanced semiconductors depend on EUV lithography. And EUV lithography depends on one company, drawing from a concentrated network of specialized suppliers, most of them in Western Europe and East Asia. This is not a supply chain. This is a single thread holding up the world. Think about what that means. A natural disaster in Veldhoven. A fire at the Zeiss mirror facility in Oberkochen, Germany. A disruption at Trump's laser plant. A geopolitical crisis that cuts off the supply of specialty chemicals or ultra-pure silicon. Any one of these events could send shockwaves through the global economy that would make the 2020 chip shortage look like a minor inconvenience. We've built the most powerful technology in human history on a foundation that is breathtakingly fragile. And there's a deeper irony here. The chips these machines produce are getting so advanced that they're powering AI systems that may eventually help design the next generation of lithography tools. The machine is beginning to feed back into its own evolution. We're approaching a point where human engineers alone may not be able to design the next breakthrough. They'll need the very chips that this machine produces to push the technology further. That is a loop unlike anything we've seen before. The machine that makes the thinking machines. The tool that builds the tools that build the future. So the next time you unlock your phone, consider this. That simple act connects you to a molten tin droplet being vaporized by a laser in a vacuum chamber, to mirrors polished to atomic perfection, to a quiet Dutch town that has become the most important industrial site in the world, to a geopolitical struggle over who gets to compute and who doesn't. This is the machine that controls the world, and it was hiding in plain sight. If you found this fascinating, think about this question. What happens when one company becomes too important to fail, too important to compete with, and too important to leave uncontrolled? Who should decide how this power is used? If this is your first time here, System Logic is where we uncover the hidden systems running behind everyday life. Subscribe so you don't miss what we uncover next.